In this video, we are going to talk about the reduction formula. It also falls as part of integration by parts. Now, if we are given functions like, let's say, for example, f of x equals sine x, or f of x equals cos x, these are very simple functions to integrate. However, there comes a point where we get, for example, f of x equals sine x exponent 5 and then cos x exponent 20. So functions of this form become very, very robust to deal with, and that is what leads us into the reduction formula. So the reduction formula is a formula that is able to encapsulate all other types of the same problem that will arise, that said that if we get higher powers, we are able to use a reduction formula to reduce it to the barest minimum and do the integration. So let's look at the case of integrations where we have x exponent n and exponent x dx. So it means that any function that comes of this form, this reduction formula will work for it. So what we will do is that let's let I of n to be equal to integral of exponent n, x exponent n, then exponent x dx. So you can see that we can easily, if we use the LIATE rule, you see that this is an algebraic function and then this is an exponential function. Algebraic function comes before exponential functions. So what we can do here is that we can let u to be equal to x exponent n. So du is equal to n times n x times n times x exponent n minus 1, then dx. Then we can let dv to be equal to exponent x dx. So if we integrate dv, we'll get v, and if we integrate exponent x, we are going to get exponent x again. So using the formula for integration by part, which is integral of u dv is equal to uv minus integral of v du. So I of n is equal to u is x exponent n, and then v in this case is exponent x, then minus integral of v is exponent x, and then du is nx exponent n minus 1, then exponent x for the v aspect dx. Nonetheless, we can rewrite this as I of n equals x exponent n, then exponent x minus, we are pulling n out since n is a constant, so n times integral of x exponent n minus 1 exponent x dx. So you can see that this integral looks in this form. However, just that here it becomes n minus 1. So instead of I of n, then all of this becomes I of n minus 1. So therefore, this integral, which is I of n, is equal to x exponent n, then exponent x minus n I of n minus 1. So this is the reduction formula for this function I of n. So any function that comes of this form, this reduction formula will be able to be used to solve it irrespective of the powers of n that we are given. So using this, let's solve the case of I of 2. Let's find I of 2. So I of 2 means n is equal to 2. So what it means is that wherever we see n in this equation, we should replace it with 2. So I of 2 is equal to x exponent n, which is x exponent 2, then exponent x minus n is 2, then I of n minus 1, which is I of 2 minus 1 is 1, so I of 1. Then let's find I of 1. I of 1 is equal to x exponent 1, which is x, then exponent x minus n, which is 1, then times I of n minus 1. 2 minus 1 is 1, so it becomes, 1 minus 1 is 0, so it becomes I of 0. So let's find I of 0. I of 0 is the least that we can find. Remember that we said that I of n is equal to x exponent n exponent x dx. So I of 0 is equal to, sorry, there was an integral here, so integral. So I of 0 is equal to integral of x exponent 0 and then x exponent x dx. Now x exponent 0 is 1. So integral of exponent x becomes exponent x, and therefore I of 0 is equal to exponent x plus c. However, we know that I of 1 is equal to x exponent x minus I of 0, and I of 0 is exponent x, then minus c. So we found I of 1. Let's find I of 2, which is what we are looking for. I of 2 is x squared, then exponent x, then minus 2 times I of 1. But I of 1 is x exponent x minus exponent x minus c. So this is equal to x squared exponent x, then minus 2x exponent x, and then plus 2 exponent x, then plus 2c. So this is I of 2. So by just using this reduction formula, we've been able to evaluate the situation where we have I of 2. And this I of 2, in other words, is the same as I of n equal to integral of x squared exponent x dx. If you do this integral, you will find that the answer is this answer. So we have this question here, which is, by forming a suitable reduction formula, show that integral from 0 to 1 of x exponent 5 then exponent minus x squared dx is equal to 2e minus 5 divided by 2e. So from the previous example, we saw that this x was exponent n. So therefore, let's let I of n to be equal to integral of 0 to 1 of x exponent n, then exponent minus x squared dx. Then we can rewrite this integral as I of n equals integral from 0 to 1. Now, I want to write this as x exponent n minus 1. But because I put minus 1 here, then I need to multiply it by x, then exponent minus x squared, all of this dx. Now, this is very important because this will become our dv, and this is what we are going to integrate. Now, so in this case, our u is equal to x exponent n minus 1. So du is equal to n minus 1, then times x exponent n minus 2 dx. Then dv is equal to x exponent minus x squared dx. So v, which is the integral of all of this, is equal to minus 1 over 2 exponent minus x squared. Now let's verify and see whether this is true by differentiating. So let's differentiate here. It's minus 1 over 2 exponent minus x squared. So if you want to differentiate it, you need to first differentiate what is inside the exponent. If you differentiate minus x squared, you will get minus 2x times 1 over 2 exponent. Then you differentiate the whole thing. If you differentiate the whole thing, it becomes exponent minus x squared. So these two and then these two will cancel. However, there is already a minus here, so there is a minus here. And if this minus 1 cancels, multiplies, it will become 1. So therefore, we are back to x exponent x minus x squared, which is what we started with. And therefore, this our integration is true. So I of n is equal to this integral. We are going to use integration by part. So it is u v. So this is our u, and then this is our vn. Vn is minus half, and then exponent minus x squared, and then u is times x exponent n minus 1, and then minus integral of v du. Then du is minus 1 over 2 exponent minus x squared, then times du, which is n minus 1, then times x exponent n minus 2 dx. So let's continue from this side. So you can see that this is equal to I of n is equal to minus 1 over 2, then x exponent n minus 1. Then we have this, which is exponent minus x squared. And then minus 1 times 1 will be plus. So plus, then I'll bring the constant half out. Then n minus 1 is also a constant, so n minus 1. Integral of, we are left with x exponent n minus 2, then times exponent minus x squared dx. So you can see something. You can see that this is the case of I of n minus 2. So I of n, however, sorry, this is evaluated at 0 and 1. 0 and then 1. So let's evaluate this at 0 and 1. Now I of n is equal to, if you put in 1, then 1 exponent n minus 1 is 1, times minus 1 over 2 is minus 1 over 2. Then exponent minus 1 squared becomes, so all of this become minus 1 over 2 exponent minus 1. Then as for the 0, because this x is here, it will go to 0. Then plus half of, then all of this is n minus 1. And then if we find this integral, remember I of n is equal to 0 to 1 of x exponent n exponent minus x squared. Here is x exponent n minus 2. So here is I of n minus 2. So this is what we find for I of n. So we found I of n to be equal to minus half exponent minus 1 plus half of into bracket n minus 1 I of n minus 2. Then I of n is also equal to integral of 0 to 1 x exponent n exponent minus x squared dx. However, we're looking for the case where I of n is equal to integral of 0 to 1 x exponent 5 exponent minus x squared dx. Then this is what we are given in the question. So it means that we are talking about the case where n is equal to 5. So if n is equal to 5, we are talking about I of 5. So I of 5, we just need to put it in this equation. So it becomes minus half exponent minus 1, then plus half of into bracket 5 minus 1 is 4. Then I of this one, n, is 5. 5 minus 2 is 3. So I of 5 is equal to minus half of exponent minus 1, then plus half of 4 is 2, 2i3. Now let's find i3. Let's put it back in the same formula. i3 is equal to minus half of exponent minus 1, then plus half of n minus 1. 3 minus 1 is 2. Half of 2 is 1. So I of n is 3. 3 minus 2 is 1. So I of 3 is minus half of exponent minus 1 plus I of 1. So we can take this I of 3 and put it back to find I of 5 in terms of I of 1. So I of 5 is equal to minus half exponent minus 1, then plus 2 times I of 3. I of 3 is minus half exponent minus 1, then plus I1. So let's expand. I of 5 is equal to minus half of exponent minus 1, then 2 times minus 1 over 2 becomes minus exponent minus 1, Then 2 times this becomes plus 2i1. So what we need to do, however, we can further simplify this. I5 is equal to, here's minus 1 over 2 minus 1. It becomes minus 3 over 2. Then exponent minus 1. Then plus 2i1. But we know that I of n is equal to integral of 0 to 1 of x exponent n exponent minus x squared dx. So we can find I of 1 from here. I of 1 is equal to integral of 0 to 1. So in this case, we replace n with 1. So that becomes x exponent minus x squared dx. And if we've already done this integral for the different case. So I of 1 is equal to, if we do this, it is minus 1 over 2 exponent minus x squared. And then all of this evaluated as 0 and 1. So let's put in the limit and see the answer we'll get. So I of 1 is equal to minus 1 over 2. And if we put in 1, it becomes exponent minus 1 squared becomes exponent minus 1. And then minus become, sorry, so here becomes minus into brackets minus 1 over 2. And then if we put in 0, exponent 0 is 1. So all of this reduced to minus 1 over 2. So I of 1 is equal to minus 1 over 2 exponent minus 1 plus 1 over 2. So let's take all of this I of 1 and put it in I of 5 to get I5. But we know that I5 is minus 3 over 2 exponent minus 1 and plus 2i1. So this is equal to minus 3 over 2 exponent minus 1 plus 2 times I of 1 is minus 1 over 2 exponent minus 1 and plus 1 over 2. So this becomes minus 3 over 2 exponent minus 1. And then if 2 multiplies minus 1 over 2, you get minus exponent minus 1. Then 2 plus times this becomes plus 1. So now minus 3 over 2 minus 1 becomes minus 5 over 2. So minus 5 over 2 exponent minus 1 and then plus 1. And this is the same as, we can rewrite this as equal to 1 minus 5 over 2e. And this is properly the same as 2e minus 5 over 2e. And that is what we're supposed to prove according to the question. And therefore, I of 5 is equal to 2e minus 5 over 2e. So let's look at the second case where we have integral of px plus q divided by into bracket ax squared plus 2bx plus c all exponent n dx. But in this case where p is equal to 0. Now immediately we put p equals 0, then it means that this integral becomes integral of q divided by into brackets ax squared plus 2bx and plus c all exponent n dx. So what we will do is that let's let I of n to be equal to integral of q divided by ax squared plus 2bx plus c all exponent n dx. And what we will do is that let's take this denominator. This is a quadratic equation, so we can complete the squares. So we're having ax squared plus 2bx plus c. So let's complete the squares. First, we need to make the coefficient of x squared 1. So this becomes x squared and plus 2b over ax and plus c over a. Now, what we need to do next is to say, find half of the coefficient of x. Half of 2b over a is b over a. You square, add and subtract, so plus 2b over ax, then plus Now, if we square b over a, we get b squared over a squared, and plus c over a minus b squared over a squared. So we have a, then all of this is reduced to x plus b over a squared. And then if we do this, let's find the LCM. The LCM is a squared. So this a will cancel one here. So we have ac, then minus b squared. So this is the completed square. So I of n actually is equal to, now I want to replace all of this by this. However, this becomes integral of q divided by, into brackets, then we have a times x plus b over a squared, then plus, now this a will multiply one of this, will cancel one of this square, so here becomes ac minus b squared over a, all exponent n dt. So having gotten this, now we cancel this one, so this is not part. So let's let t to be equal to x plus b over a. So dt is equal to dx. And then let's let phi to be equal to ac minus b squared over a. So it means that this integral I of n can be reduced to factorizing q out because a constant. Integral of 1 divided by, into bracket. Now all of this becomes t, so at squared, then plus, now phi, all of this becomes phi, plus phi, all exponent n dt, because dx is equal to dt. So the point we reached was I of n equals q integral of 1 divided by, into bracket, at squared plus phi exponent n dt. And then where we said that t is equal to x plus b over a, and then phi is equal to ac minus b squared over a. So in this case, let's rewrite this I of n as I of n equals, so let's write it here. Let's write I of n as I of n equals q, then integral of, can rewrite this as, into bracket, at squared plus phi, then exponent minus n dt. Now let's let our u to be equal to, into bracket, at squared plus phi exponent minus n. Now it means that du is equal to, pull down minus n and then subtract 1. So if we do that, we are going to get minus n, then times at squared plus phi exponent, here becomes minus n minus 1, then times, if we differentiate at squared plus phi, you get 2at. So du, sorry, here will be, there's a dt here. So du is equal to minus n, then to bracket, at squared plus phi, then minus, into bracket, n plus 1, then times 2 at dt, and then the is equal to 1 dt. So v is equal to t. We can use integration by parts. So I of n is equal to u v, so it becomes t times at squared plus phi exponent minus n, then minus integral of v du. This is du, this is v, so it becomes 2at times t, becomes 2at squared, then times minus n times at squared plus phi, then exponent minus, into bracket, n plus 1. So we have established that I of n is equal to qt into bracket at squared plus phi exponent bracket close exponent minus n minus q, then integral of 2at squared times minus n into bracket at squared plus phi all exponent minus into bracket n plus 1 dt. So this can further be simplified to, now this can be written as qt divided by into bracket at squared plus phi exponent n minus, now this is the same as, let's bring 2a outside, so this becomes, but there is minus n here, so minus n times minus q become plus, so plus 2an q, then integral of t squared divided by into bracket at squared plus phi and exponent n plus 1 dt. Now what I want to do is that I want to add phi here, so that here will be plus phi minus phi. This can be written as I of n equals qt divided by into bracket at squared plus phi exponent n, and plus, this becomes 2an q, then I want to bring a bracket, integral of t squared plus phi divided by into bracket at squared plus phi. Now here's n plus 1, so I can write here as n plus 1, then dt, and then minus integral of phi divided by into bracket at squared plus phi exponent n plus 1 dt, bracket close. So I want to push this a here so that we'll get at plus phi. So this becomes I of n equals qt divided by into bracket at squared plus phi exponent n, then this becomes plus 2n q, integral of at squared then plus phi divided by two brackets at squared plus phi exponent n, then I want to write it another one as at squared plus phi, so this is the plus 1, and then minus, this becomes 2an q, integral of phi divided by 2 bracket at squared plus phi exponent n plus 1 dt. So you see that here is at squared plus phi, at squared plus phi, let's say dt here, so it will cancel out. Therefore I of n is equal to qt divided by at squared plus phi exponent n, then plus, I want to push q inside, so 2n integral of q divided by at squared plus phi exponent n dt, then minus, I want to bring phi out and push q inside, so here becomes 2an phi, and then integral of q divided by 2 bracket at squared plus phi exponent n plus 1 dt. Remember what we said earlier, we said I of n is equal to integral of q divided by 2 brackets at squared plus phi exponent n dt. So all of this becomes I of n equals qt divided by at squared plus phi exponent n, then here becomes plus 2n, all of this is I of n, and then all of this becomes minus 2an phi. Then here's n plus 1, so it becomes I of n plus 1. I of n plus 1, the subject, is equal to, now we are dividing through by, I'll be 1 divided by 2an phi, then times qt divided by into bracket at squared plus phi exponent n, then plus 2n I of n minus I of n. So this is the final answer. We have this question here that says that I of n is equal to integral of 0 to a, then times x exponent n divided by into bracket a squared minus x squared dx, where n is a natural number and a is greater than 0. Show clearly that I of n is equal to a squared into bracket n minus 1 divided by n, I of n minus 1, where n is greater or equal to 2. And then b, integral of 2 to 4, 3x cubed minus 18x squared plus 36 minus 18 divided by square root of 4x minus x squared dx. So I of n is equal to, let's rewrite this as integral of 0 to a x exponent n minus 1. And because I put x exponent n minus 1, then I'll multiply by x divided by square root of a squared minus x squared. And the reason why we are doing this is so that we can easily integrate this part of the function, so that this is dx. So let's let u to be equal to x exponent n minus 1. So du is equal to n minus 1 times x exponent n minus 2 dx. Then let's let the to be equal to x divided by square root of a squared minus x squared dx. So v is to integrate this, and if you integrate all of this, you will get minus square root of a squared minus x squared. If you don't understand how this comes about, I've already done a video on how to integrate rational functions, so I will link it in the description, so you can watch that video and understand why this integral is like this. It's equal to, now u is x exponent n minus 1, and then v is minus square root of a squared minus x squared evaluated at 0 and then a, and then minus integral of v du. Our v is minus square root of a squared minus x squared times du is n minus 1, then times x exponent n minus 1 dx. Here's I of n. I of n is equal to minus x exponent n minus 1 square root of a squared minus x squared evaluated as 0 and a minus, so this becomes plus n plus 1, then integral of square root of a squared minus x squared, then times x exponent n minus 1 dx. Here is du. v du, here we n minus 2, so I made a mistake. This is n minus 2 dx, because du is into bracket n minus 1 x exponent n minus 2 dx. So the next thing we are supposed to do is to evaluate this part. You see that if we put in a squared minus a squared will make it 0. Square root of 0 is 0 times all of this part will go to 0. If we put in 0, because of this x, it also goes to 0. Therefore, I of n is equal to, so here is 0 and then a. This place to 0 and then a. So I of n is equal to n plus 1, then integral of 0 to a of square root of a squared minus x squared, and times x exponent n minus 2 dx. Let's rewrite this and then rationalize. So I of n is equal to n plus 1 integral of 0 to a x exponent n minus 2 and times square root of a squared minus x squared dx. But I want to rationalize this by multiplying both the numerator and the denominator by a squared divided by minus x squared, square root of that divided by square root of a squared minus x squared. So that if we do the multiplication, I of n is equal to n plus 1 integral of 0 to a, and this becomes into bracket a squared minus x squared times x exponent n minus 2. All of this divided by square root of a squared minus x squared dx. So let's break the integral into 2. So we find out that I of n is equal to n plus 1. Then integral of 0 to a. Here becomes a squared x exponent n minus 2 divided by square root of a squared minus x squared dx, and then minus x squared times x exponent n minus 2 is x exponent n. So integral, but there is n plus 1 here. Integral of x exponent n divided by square root of a squared minus x squared dx. So you see that I of n here, and we can bring a out. If you bring a out, you are left with a squared into bracket n plus 1. Then all of this becomes I of n minus 2. Then minus into bracket n plus 1. Then all of this is I of n. So we can further expand this bracket. So I of n is equal to a squared times n plus 1, I of n minus 2. Sorry, there's a mistake I made here. Here's n minus 1. So this place is supposed to be n minus 1. So all the places where we have n plus 1 is supposed to be n minus 1. Therefore, here is also supposed to be n minus 1, n minus 1, and n minus 1. And therefore, I of n will become into bracket n minus 1. And all of this is I of n minus 2. Then minus into bracket n minus 1, I of n. So I of n is equal to into bracket n minus 1, I of n minus 2. Then minus n I of n plus I of n. So you see that here is I of n, so it can cancel. So we can bring n I of n to the other side. So we have n I of n is equal to bracket n minus 1, I of n minus 2. So I of n, if you divide through by n, becomes, but sorry, there is an a squared here. So here is an a squared. There's also a squared here and a squared here. So it becomes a squared times n minus 1, I of n minus 2 divided by n. And that's what we are asked to prove in the question. We have been able to prove that I of n is equal to a squared into bracket n minus 1, I of n minus 2 divided by 2. The second part of the question says that we should solve integral from 2 to 4 of 3x squared minus 18x squared plus 36 minus 18 divided by square root of 4x minus x exponent 2. So what we need to do is to be able to express all of this integral to look like this form, and we can use the definition for I of n. So let's take this numerator and then complete the squares. So 3x squared cubed minus 18x squared plus 36 x minus 18. Let's factorize 3 out. We are left with x cubed minus 6x squared, then plus 12x minus 6. Now, what is x minus 2 cubed? This is the same as x cubed and minus 6x squared, then plus 12x minus 8. So what it means is that this can be written as 3 times into bracket x minus 2 cubed and then plus 2, because minus 8 plus 2 give minus 6. So the numerator can be written as 3 into bracket x minus 2 cubed and plus 3 times 2 is 6. Then let's come to the denominator. Let's complete the squares. So we have 4x minus x squared. So let's factorize minus 1 out. We are left with x squared minus 4x. So half of minus 4 is minus 2. If you square, you get 4. So this becomes minus 1 times x squared minus 4x plus 4 and minus 4. So we can rewrite this as minus 1 times into bracket x minus 2 squared minus 4. So this is the same as 4 minus x minus 2 all squared. So this function can be reduced to integral of 2 to 4. The numerator is what we got here, which is 3 times x minus 2 cubed plus 6 divided by square root of 4 minus to bracket x minus 2 squared. So now let's let u to be equal to x minus 2. So it implies that du is equal to dx. So this, but when when x is equal to 2, u is equal to 0. And when x is equal to 4, u is equal to 2. So this integral becomes integral of 0 to 2 of 3u cubed plus 6 divided by square root of, now this 4 is the same as 2 squared minus u squared du. Break the integral into 2. So this becomes 3 integral of 0 to 2 of u exponent 3 divided by into bracket 2 squared minus u squared du, then plus 6 integral of 0 to 2 of 1 divided by square root of 2 squared minus u squared du. You can see that this is a clear case of 3i3 using this. This is 3i3 because u exponent 3. So this is 3i3 plus. If you integrate all of this, it is sine inverse. So 6 sine inverse of u divided by 2. Now, this is evaluated at 0 and 2. This is equal to 3i3 and plus 6 times. Now, if you put in 2 divided by 2 is 1. Sine inverse of 1 is 90 degrees. Inverse of 1 is 90 degrees, which is the same as pi over 2. And then minus, if you put in 0, sine inverse of 0 is 0. So minus 0. and then this is equal to 3i3 plus 3 pi, plus 3 pi. So you've seen that we've gotten one side of the proof. So it's left with the minus 16. And that one will come from the evaluation of 3i3. But we need to take this 3i3 and put it back into this formula, because we said I of n is equal to, but a, this is a squared is 2 squared, so a is equal to 2. So I of 3 is equal to, now let's just do 3 of I of 3 is equal to 3 times I of 3, and I of 3 is a squared, which is 2 squared, times n minus 1, which is 3 minus 1, and that is 2. Then times I of n minus 2, 3 minus 2 is I of 1, divided by n, and then n in this case is 3, so divided by 3. So this 3 and then this 3 will cancel out. So we are left with 2 squared, which is 4, and 4 times 2 is 8, so 8 I1, and this is equal to 8 times I1 is the same as integral from 0 to a of x divided by square root of a squared, which is 2 squared minus x squared, a squared minus x squared. And if you do this, let me write it down here. This is the same as 8 times square root of a squared minus x squared, evaluated at 0 and a. Now, if we put in a, we will get 0. But if we put in 0, we are going to get a. So this is the same as 8a, but a is equal to 2, and this is the same as 8 times 2, which is equal to 16. So at the end of the day, you see that this one, we are saying that the integral is 3i3 plus 3 pi. 3i3 is 16, so this is equal to 16 plus 3 pi, plus 3 pi. And that is what the question asks us to prove.